I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of June 2023. This question is from the section Linear Algebra and the question is related to a linear operator on R cube. This question is from the part B, which is a multiple choice question. It carries 3 marks. The question ID is 704028. Right. The given question is, let T be a linear operator on R cube. Let f of x belongs to R bracket x, that is the polynomial ring in one indeterminate x over the field of real numbers, and that is f of x belongs to R of x, denote its characteristic polynomial. Consider the following statements. Statement A. Suppose T is a non-zero linear operator and 0 is an eigenvalue of T. If we write f of x is equal to x multiplied by g of x in R of x, R bracket x, then the linear operator g of t is 0. Statement B. Suppose 0 is an eigenvalue of t with at least 2 linearly independent eigenvectors. If we write f of x is equal to x times g of x in R bracket x, then the linear operator g of t is 0. The question is, which of the following is true? We are given 4 options. Option 1, both A and B are true. Option 2, both A and B are false. Option 3, A is true and B is false. Option 4, A is false and B is true. Let us now discuss the solution of the problem in detail. We have a linear operator T on R cube, that means T is a linear transformation from R cube to itself. Given f of x belongs to R bracket x is the characteristic polynomial of T. And here we have the statement A. Now, we discuss the statement A. Given T is a non-zero linear operator and 0 is an eigenvalue of T. We are also given f of x, which is the characteristic polynomial of T, is equal to x times gx in Rx. Our question is the linear operator g of t 0? That's the question. Is it 0? Now, this is not true. When the remaining 2 eigenvalues, one of the eigenvalues is 0, the remaining 2 eigenvalues are distinct, non-zero real numbers, say 1 and minus 1, then this is not true. That is, g of t is 0 is not true. So let's say, now let t be defined by t of xyz is equal to the 3 by 3 matrix 0, 0, 0, 0, 1, 0, 0, 0, minus 1 multiplied by the column vector x, y, z. Then the matrix of T with respect to the standard basis is this matrix 0, 0, 0, 0, 1, 0, 0, 0, minus 1. And f of x, the characteristic polynomial of T, is 0 minus x multiplied by 1 minus x multiplied by minus 1 minus x. That is minus x into 1 minus x into minus 1 minus x. That is x into 1 minus x into 1 plus x. You note down that the characteristic polynomial of T is the product of distinct linear factors. Okay. Its minimal polynomial, mt bracket x, is the characteristic polynomial itself, that is f of x, because the minimal polynomial of T will have the same eigenvalues, but it will be the product of distinct linear factors like this. Because f of x is the product of distinct linear factors, the minimal polynomial is the characteristic polynomial itself, and therefore that is x into 1 minus x into 1 plus x. Agreed? Agreed. Now, f of x, it is given f of x is equal to x times g of x. So, what is f of x is equal to x times g of x? Then what will be g of x? X times g of x. So, g of x will be 1 minus x into 1 plus x, that is 1 minus x square. Now, and g of t, if you substitute for x is equal to t, there is 1 minus t square, is not 0. Is not a zero linear operator. Why? Because the degree of the minimal polynomial, what is the minimal polynomial here? X into 1 minus x into 1 plus x. What is the degree? Degree is 3. So, since the degree of the minimal polynomial is 3, therefore, it will not satisfy any polynomial. It will not annihilate any polynomial whose degree is less than the degree of the minimal polynomial. Here g of x is, the degree is 2, therefore this cannot happen. Agreed. That means your statement A is not true. Thus, the statement A is not true. Okay. Let's now move to the next slide for the discussion of statement B. So, we have the linear operator T on R cube, given f of x belongs to the R of x, R bracket x is the characteristic polynomial of T. Statement B states, suppose 0 is an eigenvalue of T, yes, with at least 2 linearly independent eigenvectors, and if f of x is equal to x times g of x in Rx, then the linear operator T, the linear operator g of T is 0. Is it? Is the linear operator g of T 0? That's the question. Okay. We have 0 is an eigenvalue of T, and it is given with at least 2 linearly independent eigenvectors. That implies with at least 2 linearly independent eigenvectors, the eigenvalue is 0. Then the geometric multiplicity of the eigenvalue 0 is at least 2 linearly independent eigenvectors, therefore it is greater than or equal to 2. Now we ask the question, what about the algebraic multiplicity? The algebraic multiplicity is always greater than or equal to geometric multiplicity, therefore the algebraic multiplicity of the eigenvalue lambda is equal to 0 is also greater than or equal to 2. Anyway, let A be the matrix of T with respect to the standard basis. Geometric multiplicity of lambda is equal to 0 greater than or equal to 2 will imply dimension of the null space of A minus 0i, A minus lambda I, because the geometric multiplicity is corresponding to the eigenvalue lambda is equal to 0, the dimension of the null space of A minus lambda I, where lambda is 0. That is the geometric multiplicity definition, is greater than or equal to 2. So that means this is denoted by the nullity of A. 0, A minus 0, the nullity of A. Eta of A greater than or equal to 2. Now recall rank-nullity theorem. Rank of A plus nullity of A is equal to 3. Right, it is from R cube to R cube. It is 3 by 3 matrix. Number of rows, number of columns are 3. This implies rank of A is 3 minus nullity of A. Because nullity of A greater than or equal to 2, 3 minus nullity of A is less than or equal to 1. So rank of A is less than or equal to 1. Bear in mind. Now the geometric multiplicity of the eigenvalue lambda is equal to 0 is greater than or equal to 2 will imply the algebraic multiplicity of the eigenvalue lambda is equal to 0 is also greater than or equal to 2, because the algebraic multiplicity is always greater than or equal to geometric multiplicity corresponding to the same eigenvalue. Now, if the algebraic multiplicity of the eigenvalue lambda is equal to 0 greater than or equal to 2, then we can write down the characteristic polynomial of t, that is f of x, is equal to x cube when the algebraic multiplicity of lambda is equal to 0 is 3, because it is greater than or equal to 2 means it may be 2 or 3. So when it is 3, x cube is f of x. When the algebraic multiplicity of lambda is equal to 0 is 2, then it will be x square, and there will be one more eigenvalue, let us say a multiplied by x minus a, where a not equal to 0. Right. So we are given f of x is equal to x times g of x. X times g of x is equal to x cube will imply g of x is x square. X times g of x is x into x square into x minus a will imply g of x is x into x minus a. So given f of x is equal to x times g of x will imply g of x is either x square or x into x minus a. Our question is g of t, that is t square, is it 0? Is g of t multiplied by t minus ai, is it 0? That we will discuss in the next slide. Right, we have the characteristic polynomial there. Let m of x, the minimal polynomial of a. Here, whether we talk about the linear operator t or the matrix A, it matters the same. Right. Let m of x be the minimal polynomial of A, and we know the minimal polynomial of A, the minimal polynomial always divides the characteristic polynomial. Therefore, m of x divides f of x. So m of x, minimal polynomial of x, divides x cube means what are the possibilities? M of x is x or x square or x cube. M of x divides x square into x minus a means what? M of x is either x square into x minus a or x into x minus a. These are the possibilities of the minimal polynomial of x. Suppose minimal polynomial of x is equal to x cube, then a is equivalent to the JCF, Jordan canonical form, because m of x is x cube, it contains only one Jordan block of size 3, that is 0, 1, 0, 0, 0, 1, 0, 0, 0. And observe now, what is the rank of A? There are only two linearly independent rows are there. So rank of A is 2. But the rank of A is less than or equal to 1, which we have seen in the last slide. Therefore, it's a contradiction to the fact the rank of A is less than or equal to 1. So this will not be possible. Suppose m of x is x square into x minus a, then A is equivalent to the Jordan canonical form for corresponding to x square. We have a Jordan block of size 2, that is 0, 1, 0, 0, corresponding to 0. X square means x minus 0 whole square. And corresponding to x minus a, only one block of size 1, that is a. So the remaining are zeros. Now again look at that. There are only two linearly a not equal to 0. Two linearly independent rows are there. The rank of A is 2. It's a contradiction to the fact the rank of A less than or equal to 1. So this also is not possible. Therefore, what are the possibilities? In all the remaining cases, m of x is x or x square or x into x minus a. Agreed. And the matrix A annihilates the minimal polynomial. Therefore, m of A will be 0. That means m of A is 0 means A is equal to 0 when m of x is equal to x. When m of x is equal to x square, m of A is a square is equal to 0. In the remaining case, a into a minus ai, small ai, is equal to the 0. A is equal to 0 will imply a square is equal to 0. So we write down only two conditions. A square is equal to 0 or a into a minus small ai is 0. Given f of x is equal to x times gx, look back here. This we have already discussed. This means g of x is x square or x into x minus a. Now see, what will be g of a is a square, which is 0. We have already seen. And g of a is a multiplied by a minus ai is 0, which we have already seen. So in any case, g of a is 0. So whether we talk about a or t doesn't matter much. Therefore, g of t is 0. So when f of x is written as x into g of x, then the linear operator g of t is 0. Therefore, the statement B is true. So what's our conclusion? Our conclusion, that is our answer, is option 4. That is, statement A is false and the statement B is true. So that is the detailed discussion of the solution of the problem from the section Linear Algebra, which is related to linear operators on R cube. And it requires some knowledge of Jordan canonical forms and some knowledge of minimal polynomials and their properties and so on and so forth. I am sure that you have understood the solution of this problem. I thank you now for watching this video. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.